When we introduce time series data, we discuss its characteristics. And one thing we draw your attention to is the presence of serial correlation among error terms, because that's a violation of OLS assumption. So when a variable exhibits correlation over time, we say it is autocorrelated or serially correlated. So that's definition. We need to check whether there is an autocorrelation among error terms when we run a regression model, because we don't want to violate that important assumption. So here are the tools that we can use. We can use either the case order sample autocorrelation, or we can use a correlogram. That's basically a visual demonstration of the sample correlation coefficients. And we can also use two tests. One is the Lagrange multiplier test. Is suitable for any orders of autocorrelation. We also have this DW test. It is designed for first order autocorrelation test, very popular in the old days, but it's used less frequently now because the LM test or Lagrange multiplier test is more flexible, it's more useful. So let's take a look at them one at a time. So suppose we would like to test the hypothesis of rho k equals 0, or the case order of correlation among those variables is 0, which means there's no autocorrelation. And we can calculate our test statistics using this formula. So all we need are the sample autocorrelation, sample correlation coefficient, and the number of observations. We use T here, just wanted to highlight the fact that we're dealing with time series data. So that those are data collected from T periods of time or T points of time. So after standardization, this correlation coefficient, standardized correlation coefficient follows normal distribution, standard normal distribution, so we can perform the test. And RK can be calculated in this way. So those are standard formula to calculate correlation between two variables. I will leave it to you. And the computer can help you to generate that coefficient. So we still use Occam's rule, same set of data. And we would like to check whether the correlations are significant from 0. So from the regression model that we estimated before, or based on the set of data that you can find from our Moodle page. And we estimate the R1, R2, R3, and R4 are as follows. So the test statistics can be calculated accordingly. We know the critical value of our test at the 5% level is 1.98. So our conclusion is, G, this is the variable of interest, by the way, the quarterly growth rate in US GDP exhibits significant serial correlation at lags 1 and 2. So for lags 1 and 2, we have the test statistics that are significantly above the critical value. So we're going to reject the hypothesis and conclude that the correlation coefficients are not 0. So if you use this correlogram, which is usually automatically generated by computer software, so you can request it, and the software can calculate correlation coefficient and visually demonstrate, okay, at which lag the test statistics actually are beyond the boundary. So the boundaries, upper bound, the lower bounds, are actually calculated based on the test formula that were introduced in previous slide. So you just compare the correlation coefficient and with the boundary to see which one is above the boundary. For those that are beyond the boundary, those are significant lags. And you have the same conclusion as we did before by looking at the formula only. So we have lag 1 and the lag 2 with a significant autocorrelation coefficients. So that's a correlogram. We also have another example, that's Phillips curve. Is a theory in economics to investigate the relationship between inflation and unemployment rate. So the relationship is as follows. Left-hand side, our dependent variable is inflation rate. Right-hand side is DU, the variable that we used in the previous example. So that's the first difference of unemployment rate. On this slide, I also give you two line chart or time series line chart. So that's the data from Australia. Left-hand side, that's the price inflation, so INF over time. Right-hand side, that's the change of unemployment rate, so that's DU. Visually, the relationship isn't that clear, so let's see what the model or the equation can tell us. So if we run the regression model, and this is OLS, by the way, we basically were treating this time series data as cross-sectional data. We didn't pay any attention to the time series nature of this data set. So we estimate this regression model, then we would like to check the residual to see whether there's any serial autocorrelation problem. If the answer is yes, this model is not going to be valid because we violate the assumption behind OLS, the technique we used to obtain those coefficients. So the first thing we need to do is to calculate the kth order autocorrelation coefficient for the residual. So we use the residual from this regression model and then use this formula. Notice that we do not have the mean of residual at different period of time, t or t minus k, in this equation, because by construction, the average of residual terms is 0. So they just disappeared. And the value at the first 5 legs are as follows. I give them on the slide. So they range from 0.549 all the way to 0.339. So all of them looks pretty large to me. And the significant bounds are calculated using the way that we mentioned before. So it is 0.21, which means anything that is above that bound we'll consider to be significant. So software, at least at Stata, can either give us the statistics or give us a visual demonstration illustration of the relationship. Here, those bars and the dots shows us the value of those correlation coefficient estimates for different legs, so like 1, 2, 3, 4, 5. And on this slide, we also showed a confidence band calculated based on a formula over there, Bartlett's formula. This is not the best one. As a matter of fact, there isn't such thing like the best one. We always use the one that is suitable. So this is for your reference only. You can plot this 0.21 line over there and check which leg is significant. I mean, either case, you should conclude that at least up to leg 4 or leg 5, the correlation coefficients are quite large and they are significant. They are, at least the first 4, they are above the boundary or the band, so they're significant at 5% level. Now let's introduce this LM test. It's a joint test of correlation at more than one leg. So if you are not just worried about one leg or leg 1 autocorrelation, you're worrying about longer legs autocorrelation, LM test is the one to use. So in a simple linear regression model like this one, the one that we estimated on previous slide, if residuals are correlated, then if they are correlated, basically means, for example, row 1, row 2, row all the way to row P, they are now 0. That basically means, okay, ET or residual, current residual is correlated with the past residuals. If that's the relationship, this has to be put into the picture, which means we need to insert ET into this equation, and that gives us this. So once we have this, we rearrange it. So essentially, we subtract YT hat from both sides of the equation. So left-hand side, we have ET's estimate. Right-hand side, you rearrange it, you have this. So this is the regression model to be estimated. And without showing you any technical details, the R squares from this regression model and the number of observations from this regression model can be used to construct a test statistics, and that will tell us whether there's a higher order of autocorrelations in this regression than this one. So essentially, that's our test equation. Note that we point out the fact that if you have lagged variables in your regression model, you lose observations. Which means, for example, in this one, ET minus Q hat will have Q minus P will have P number of missing value at the beginning of the data set. So you won't be able to use the first P observation because there are missing variables. There are 2 ways of handling this. One is to simply just delete any observation with a missing value. That basically means the first P observations are gone. Your sample size will be reduced by P, the number of lags or the length of lags that you're considering. So that's the first one. Second, you can set the initial value to 0, then use all observations. This is commonly used when the sample size isn't that large, and it is reasonable to assume that older data have much less influence compared with the more recent data. So even if our estimation is wrong for those early initial values, those first P values, they're 0, set them to 0, right? Even if they're wrong, over the time, their impact is negligible. But it helps us to save the number of observations, which to a certain extent will increase the robustness or reliability of the estimation. So this is a compromise. In many cases, there isn't significant difference between those two, which means the first several observations are not that important in this type of analysis. Let me show you why is that, okay? So to test H0, whether rho equals 0 and P equals 1, which means we only consider first order autocorrelation, only one period ahead. And the critical value is 3.84 from statistical table. That's based on chi-square distribution with 1 degree of freedom. And we use method 1 and method 2 to calculate the test statistics. So those R squares are from 2 regressions. One used T-1 observations, another one used the whole data set. We set the first observation to be 0. So you may notice that the test statistics or the R squares are quite similar. 0.3102 for the first regression and 0.3066 for the second regression. And the test statistics are quite similar as well. They are not marginal in terms of the comparison with the critical value. So in both cases, the null hypothesis is rejected. We conclude the errors from this linear regression model are serially correlated. So we have some issue with that. You may extend the lag length to beyond 1. That's the benefit that LM test can offer over DW test. So if we test P equals 4, you're going to lose 4 observations. So you may see the difference between those 2 regressions are bigger compared with the previous one. But once again, the statistics are quantitatively different, but qualitatively identical, in the sense that it doesn't matter which one you use. You're going to reject the null hypothesis at a very low level. Okay, so even at a 1% level, you're going to reject the null hypothesis. They're simply very large, which means the errors are serially correlated up to lag 4.